Hello, my name is Masao Sakuraba. Thank you for your interest in this video. Today, I'd like to talk about this title, Epitaxy and In-Situ Doping of Group 4 Semiconductors by Low-Energy Plasma CVD for Nanoelectronics. This is outline of my talk. First, background and subject, and then our plasma CVD processing. Second, I will show you some typical experimental results of epitaxy and in-situ doping. Third, I will show my new concept of crystal structure transformation and silicon nanosheet. And finally summarize my talk. First is background and subject. For next generation silicon array size, high-performance transistor with lower power consumption becomes important. In such a trend of semiconductor devices, process development for quantum tunneling structure formation on the silicon area size will be required and will enable a tunnel transistor and resonant tunneling device. A tunnel transistor is a candidate of low voltage and high efficient switching device for next generation. Aiming at the vertical channel type seems to be natural for me by using epitaxy. In order to realize this device, many issues can be imagined. For example, most difficult process seems to be fine pattern formation of 10 nanometer order thin or wire structures. Additionally, gate stack formation for extremely low voltage switching is necessary. Anyway, from epitaxy side, low temperature epitaxy has an important role in definition of channel length and abrupt doping profile. Corresponding energy band structures are considered like these figures. Quantum tunneling is highly sensitive to tunneling distance, and the distance should be precisely controlled in nanometer order. Therefore, I believe that key technology is energy band modulation using nanometer scale heterostructure and local doping. In this way, we should suppress intermixing at interfaces. As another kind of quantum effect devices, we have fabricated resonant tunneling diodes. Negative differential conductance is attractive for realizing new functions by fewer devices in electronic circuits. For lower germanium fraction heterostructure, it was difficult for us to achieve room temperature observation of current peak. However, by increasing germanium fraction above 50%, such as 70%, we have succeeded in room temperature observation of current peak. Unfortunately, the peak was so small, and this result is still far from circuit application. I think this is due to the large lattice mismatch, and the intermixing during epitaxy is considered at the gross temperature. Therefore, further increase of germanium fraction seemed for me highly challenging in conventional process by using thermal CVD. In this way, key technology is energy band modulation using nanometer scale heterostructure and local doping with suppressed intermixing. Therefore, in our group, Low energy plasma CVD process has been investigated for lower temperature epitaxy. Here, I'd like to show our plasma CVD apparatus for low temperature epitaxy. Low energy argon plasma is generated by electron cyclotron resonance (ECR) and induces surface reaction of reactant gases such as silane, germane, and so on. This has enabled us to achieve epitaxial growth of group 4 materials and in-situ doping without substrate heating. By using temperature monitor device, we have confirmed average temperature of substrate surface region. The surface temperature tends to rise by higher power microwave and longer time irradiation. But by employing lower microwave power, it has been clarified that we can keep the surface temperature below 100 degrees C. In our apparatus, actual argon ion energy distribution has been confirmed. The ion energy is suppressed below 10 eVs. Moreover, by changing microwave power and argon pressure, we can control the peak energy. Next, recent advancement in low-energy argon plasma-enhanced epitaxy of silicon-based group 4 alloys on silicon substrate is shown. This is a typical TEM picture of silicon and silicon germanium alloy heterostructure. Germanium fraction is about 60%. From arrangement of bright dots, epitaxial growth is realized even without substrate heating. These figures show XRD reciprocal space maps from silicon-silicon germanium alloy heterostructure on silicon substrate. Line-shape diffraction pattern is aligned to the silicon substrate position, and this indicates the silicon germanium alloy is lattice matching to silicon substrate. For the thicker films than 24 nanometers, the diffraction pattern tends to shift and to be diffused. This indicates the film strain becomes relaxed. This trend is not so different from the case of conventional thermal CVD. This figure shows current voltage characteristics of a silicon p-n junction diode fabricated on N-type silicon with and without silicon germanium alloy insertion. Especially to evaluate effectiveness of our plasma CVD process, the p-n diodes were fabricated without high temperature process. Although reverse bias current level seems slightly high, we can observe good rectifying characteristics with an ideal slope of 60 mV per decade at the forward bias. Additionally, modulation effect by bandgap narrowing in silicon-germanium alloy has been successfully observed from the voltage shift. This is a good news for us. By eliminating high temperature process, these results indicate a possibility that the part of semiconductor device fabrication can be more simplified, that is, smart process, and keeping device performance. For example, waiting time for heat up and cool down, and cross-contamination problem, which is caused by thermal diffusion, might be eliminated. In the same manner with the silicon-germanium alloy, we have also investigated silicon-carbon alloy epitaxy on silicon. These figures show electron diffraction patterns from silicon-carbon alloy films grown on silicon for various total pressures of silane and methane. These figures show 3D and 2D plots of XRD reciprocal space map for a silicon-carbon alloy film. The shape of diffraction peak apparently indicates that the deposited film is lattice matching to the silicon substrate. However, film strain is not tensile but compressive, similar to the silicon-germanium alloy. This is an unexpected and strange result because carbon atom is smaller than silicon atom, so we need further investigation, but carbon incorporation at interstitial site is considered at present. Next, I'd like to move on epitaxy of boron atomic layer doped silicon. Atomic layer doping in epitaxy is another concern for achieving abrupt doping profile in modern semiconductor devices. This seems to be effective to realize a low-resistive ultra-thin film. But I don't know whether ideal atomic layer doping has been realized or not. In my understanding from the text of semiconductor physics, acceptor in semiconductor crystal modulates local energy bands. Therefore, when acceptors are overlapping with neighboring atoms, they will form a deep quantum well at the valence band side. The quantum well will strongly confine carriers and restrict perpendicular transport. This can be also applied to precisely controlled quantum tunneling structures. By using our low-energy argon plasma CVD, boron atomic layer doped silicon was deposited on silicon without substrate heating. Electron diffraction and AFM analysis show that the films are epitaxially grown and the surface roughness is not so bad. Sims profiles of boron concentration also show single boron atomic layer is confined in very thin region. Peak boron concentration can be confirmed to be far above 10 to the 21st per cubic centimeter and close to 10 to the 22nd. For two types of silicon wafers with or without tensile strain, the profiles are almost the same in this case. In spite of very high peak boron concentration, high carrier concentration above a few percent was observed. Of course, higher activation ratio should be pursued for the higher performance tunnel transistor, so we need further investigation on the high activation of doping by our plasma CVD. As the final topic of my talk, I'd like to show you a concept of crystal structure transformation in silicon nanosheet. As well known in the surface science, surface atom reconstruction occurs on clean silicon surface. Until now, I have surely confirmed dimerization through observation of electron diffraction pattern like this. These pictures show bird's-eye views for three atomic layer thick silicon 100 one by one and transformed pentasilicene by a ball and stick model. In my imagination, the transformation can be achieved naturally by long-range coordinated and double-sided reconstruction, in other words, dimer formation and twisting of mid-layer atoms. All of dangling bonds, except for dimerization, are intentionally omitted in these models. Therefore, the dangling bonds should be terminated by some atoms, for example, oxygen atoms in gate insulator in device applications. In relation to this concept, designing a silicon-based two-dimensional structure analogous to hexagraphene and pentagraphene has recently attracted concern in the material science field. From very earlier literatures, pentasilicene seems to be a part of three-dimensional crystal called as silicon clathrates. If we can deposit silicon atoms on pentasilicene and induce further reconstruction, we might realize a new type of silicon nanosheet, including silicon-20 fluorines. By trapping an impurity atom in the individual cage of fluorines, electronic properties will be altered drastically. In order to create higher performance semiconductor devices, I believe such efforts in new material processing will contribute. Finally, I have to summarize my talk. Today, I have shown these things briefly. By low-energy plasma CVD, epitaxy and in-situ doping of group 4 semiconductors have been investigated for electronics. Low-energy argon plasma can induce epitaxy of strained silicon germanium and silicon carbon alloy on silicon 100 without substrate heating. In-situ boron doping in silicon epitaxy has been also enabled as well. By P plus N junction formation under low temperature, we can observe good rectifying characteristics and effective bandgap narrowing in the silicon-germanium alloy. For higher performance of semiconductor devices, new concept of crystal structure transformation in silicon nanosheet is suggested. Thank you for your kind attention.